Okay, so now we are going to do the next problem, sixth problem. So here the interesting question is that you're asking if you remove this bird from the consideration, then would it be an abstraction? Notice that removing doesn't necessarily mean abstraction, because if you remove a constraint, then it becomes an abstraction. Here, by removing the bird, you are actually removing a faster way for the bug to get around, and so in fact it constrains the problem more. Okay, so in essence what you are doing is that uh, the newer problem is more constrained than the older problem, and so actually the optimal path in the newer problem might be longer than the optimal path in the older problem, and so a heuristic for the newer problem won't be admissible for the older problem. So the answer we are looking for is false, because when without the bird, the bug may have to do more action to get to its goal. Okay, so that's basically the reason for why it is not actually admissible. So the trick here is that I made it look as if removing of the bird is like removing of a constraint, but removing of the bird is actually making the problem more constrained. So this is the thing. So if you bomb a city, then the life of the people in the city become harder, even though of course the city is now like flat and there are no trains and no buildings, etc. That's not actually abstracting the city. It is in fact making the city environment more constrained, because now they have much fewer options to travel, because that's basically what happened to this poor bug here. Now in the context of this min-max thing, all I was looking for is to say that essentially that in you doing min-max, essentially sorry, so I should not be saying this. When you're doing min-max, the bottom of the evaluation values in the bottom are taken, you're taking mins and maxes of them to get to the top. And so when you're doing mins and maxes, basically in the end the backed up value at the root node would be some value from the bottom or the leaf level. So what that means in a sense is, if everything here is even, then this has to be even too. It can't be odd. Okay. So the answer here is no, it's not possible. No, it is not possible for the backed up value to ever be odd in this case. Of course, a lot of you said you can use expective max, but then expective max is not min max. Okay, which you did get partial points if you said expective max, but really I was hoping that you'll realize that min max will basically take up something that one of the values that is actually true at the leaf node. So then this one is straight from the eighth question is straight from the lecture. The reason for going deeper is because essentially as you go deeper you might see traps, and the traps will essentially ensure that the backed up value is better than what the evaluation function is telling us. right? So that's ultimately what happens. So it's not that the evaluation function is becoming more accurate, it's just that you see traps. Okay, so the answer is false. The reason we do better by going deeper is because most interesting games have shallow traps that the search detects. Okay, so that's basically about 8. The ninth one, again, this is just a definition of convex functions. Convex functions, they don't necessarily have the gradient any easier to compute. All that you care about a convex function really is that it has a single global, single minimum. And then so you cannot get stuck in local optima because there's only one optimum. Okay, so essentially the answer here is false. The reason we like convex functions is because they have no local minimum. They have basically, I would probably say they have a single extremum, but it is, extremum basically minimum, maximum. Then finally for the MDP thing, the answer for MDP essentially is, it has nothing to do with being able to observe. In fact, MDP agents, to even do their policy, have to know which state they are in. The reason MDP agents are looking for policies is because after they do an action, they can't be completely certain which state they will go. They can only be probabilistically certain. And so you really need to know what to do whichever state you get into. So the reason they actually search in policy space for policies rather than for sequential paths is because their actions are stochastic. So the answer again here is false, because false, and the reason MDPs look at policies is because they deal with stochastic actions and can't be certain about the state after okay. So that's basically it, okay, as far as this is concerned. Okay.